Hello everyone, I'm Katherine Rocha, and today I'm going to be talking a little bit about finding your Codebases C++ roots. So this is basically taking genealogy and applying it for C++. So who here knows what genealogy is? Raise your hand. Cool. So genealogy is kind of finding where your family came from. It's taking and looking at your family tree, kind of trying to start where you're at now and work backwards. So go up to your grandparents and then go up past there and connect the dots. And the big thing with that is we don't know everything here. So we have a lot of holes and we're trying to figure out where the holes meet and how to actually connect it. And the big thing also is this is a story, so it's more about the story than it is about what's actually going on. Cool. So the big link between genealogy and C++ is that we don't actually know all the information that we're dealing with here. So in C++, when we're looking at legacy code in our code base, we don't know everything that any previous developer did, why they did it, how they did it. We're kind of trying to take the information that we have in the code, in the documentation, and figure out what's going on. So this is kind of trying to solve a mystery and deal with code bases being this little micro history in C++, as well as like family trees are to our historical data. So we can kind of learn from how genealogists tend to link everything together, so that way we can write our code better and link everything together from the C++ side as well. So who am I? I'm a software engineer. I volunteered at CppCon and C++ Now, and I've given 2 lightning talks on kind of an entry-level view of getting into industry and kind of the things that would be beneficial as an entry-level engineer. Though I'm kind of getting to be a little bit less entry-level at this point now. But yeah, so with that, I've started joining my family's hunt for their history. I've joined and working with my family for figuring out our family tree, and we actually have 2,349 people in our tree. So like pretty large number, a lot of different holes, and you're starting to get up to the point where documentation is all digitized, trying to figure out what's going on in languages that I don't know. And so that makes it a lot more difficult, and in languages that sometimes have changed so much that they don't mean the same thing today that they do back then. Cool. So here's kind of our first pass at taking genealogy and applying it to our code. So we're gonna look at naming. So C++ ancestors and C++ variables and ancestor names have patterns in common, right? Like when we go up, families tend to name their kids the same style, especially as you start to look back in history, which is very similar to variable names. We name things kind of similar. So here's an example, and I want you to see, so this is part of my family tree. See if you see kind of there's a pattern in here and something that feels a little bit weird. So if everyone wants to give me maybe a thumbs up if you start to see it. Cool. So if I highlight it, we have 3 kids from 3 of the kids and different parents all have the exact same name. Now this gets a little bit funky because if they were all, let's say, at their grandparents' house and went outside, so this is all off of the same census. So you could have all 3 kids living in the same house. So if you went outside and called their name, you could have 3 of them show up. And they all could have about the same birthday as well. So if they're within a year apart, suddenly it's like, who are we actually referring to when we're trying to figure this out? Does this sound a little bit like trying to deal with C++ and figure out which variables are which? Cool. So to make it a little bit more clear, if we move it to UML, which is something that I feel like we're a lot more comfortable with. In UML, it looks even worse. And then if we highlight it, it's like, well, that's rough. And so with this pattern, actually what happened is this is part of my German-Russian ancestors, and you have the grandparent is the name of the second born son, is where you get that naming coming in. So that's where we see that common grandparent getting named. So since we have that pattern, that's what's causing this issue. So when we look at real code, we notice it happens everywhere. We have it a lot with math, so if you're doing anything with algorithms, anything like that, we're gonna start having all these duplications of names just because we have these issues. You can also see it in C++20 concepts, as well as if we have actions and objects. So if we're running like a run function, how many different places can we do a run function that does something? So here's a look at a namespace that's a math namespace, and it has a couple of different functions in it that are all named square or something like square. And so this is confusing. So how are we going to end up dealing with this issue? Well, we'll probably end up looking at the context clues, and we're really lucky because we have IDEs that allow us to kind of jump backwards and figure out, okay, this is the function that's being called here, and this is why we're doing the things that we're doing. But when we're looking at our code and seeing it, it becomes really hard to figure out what the actual intention is versus what we're actually ending up doing. And so this can be really difficult to understand and really difficult to figure out. And so we're going to use context clues in the short term to figure out why we're doing the things that we're doing. And then in the long term, we're going to need to figure out a better solution because this isn't really viable long term. Cool. So to deal with it, we're going to need to go against the status quo. And this is something that we see everywhere. And with the kid example, we're going to need to have someone who decides maybe we don't name all of our kids based on which family member is going up the tree because we're going to start having duplication. And this isn't working too well. So we have to figure out that there's a reason, there's an issue, why there's an issue, and what we're going to do in order to fix that issue. And this requires actually figuring out how to apply it across the entire code base. So this requires not just one engineer being like, this isn't great, we're going to do something different, but requires every engineer there being like, we're going to do something different. And it's probably not going to work. Like odds are it's no better than what we tried before. But if we don't have that consistent work on it, then we're going to have issues figuring out what's actually going on. Cool. So now here's our second example. So we're going to be looking at the people and trying to figure out what's going on there. Okay. Yeah. So with the people, we have our software genealogists or engineers. So we're trying to figure out kind of what's going on with our software engineers. And just like genealogists attempt to understand people, software engineers attempt to find and understand code. So we're going to look at the software and attempt to understand why was it done, how was it done, and understand those software engineers of the past. Almost like how we're finding our family tree of going up the tree and finding, okay, here's my ancestors. With code, we're doing the same thing of looking up the tree and saying, who was here before me and what did they do and why did they do it? So this is a principle that's used in genealogy. It's called the fan principle. And we're going to kind of twist it a little bit and use it for looking at source code. And this is kind of going to change how we end up trying to look at the different people interacting with our code and figure out how we can look at it better. So the fan principle is friends, associates, and neighbors. And these three groups of people are kind of how you can group everybody who ends up interacting. So our friends are people who we choose to interact with. So that's everyone here. That's at a conference, you're choosing to talk to them. Life's good, we can all interact. Associates are people who are on the same project. These are those people who you're probably going to end up having code reviews with, who are all interacting in the same code base, and you'll tend to run into their code all the time. And then neighbors are people at the same company. So this is, you may have someone who you talk to on the same company who has these ideas, and you'll end up applying them to your code base from their code base. But you have a lot more ease of that information end up going from one place to another. Or it could be as simple as having corporate end up being like, you need to do this, and everyone across the group ends up having to do that. Cool. So then in order to figure out what each group is doing, we're going to use the 5 W's. So who, what, where, when, and why, to figure out kind of why people are doing the things that they're doing and what's actually going on and how we can figure out what each of these people are doing. So for what, it's what do they specialize in? And the big thing with this is we have various levels of people who know C++ and various amount of knowledge that people end up using for C++. So the big part of this is what did they specialize in? What were they working on? How did they work on it? And maybe they wrote C++, but not primarily. Maybe they mostly wrote Java and sometimes ended up getting an assignment in C++. That's going to write very different code than someone who writes C++ day in and day out. So kind of understanding why they did the things that they did and like where they actually specialize is going to determine kind of how that code ends up working. For when, we have when were they there. So this is kind of interesting because we have this whole mess of they may have been in the code base at a certain time, they may have been employed at the company at a certain time, and that can make it kind of hard to figure out what's actually going on here. So you know, okay, maybe they were working in a certain C++ version. That's why when I see their code, they may look like they're writing C++ 03 when it's actually C++ 17 now, because end of the day, that's the version they're working on and no one else has updated the code. You also have what style version. So the style that's used in the code base can change throughout time as we decide that maybe we don't want 4 spaces, we want 2, and that'll change how your code actually works and what's actually going on here. And so that's gonna change how the code looks like and what you're expecting to see. Another big thing is what the workplace was like then. So now we're getting into more hybrid and remote workplaces versus working in the office. So when you worked in the office, you had your cube mates, and that's where you're gonna end up seeing information getting passed on is someone finds something and they tell their person sitting next to them because that's the first thing that you do. And so if that happens, that's gonna make it kind of hard to figure out, like if we're in a hybrid situation now, we aren't gonna have as much of that information. As well as what were the documentation guidelines like then? So we have, were they actually supposed to document? Maybe they were required to comment every couple of lines. So that's why you see these really redundant comments. As well as we can have, as you go back in time, there's points where there was a lack of code reviews and there was a lack of unit tests. So that can kind of influence how code works and the types of code that you saw actually being pushed up. Cool. And then next is where did they work on the code? So we kind of have a bunch of different types of programmers in the room. So we have those people who ended up working on mostly one area, they're specialists, that's where you expect to see them, as well as people who are a little bit larger, they're working on like a variety of different areas. You may see them work on one area more often than another. And so we kind of need to see and understand what's going on there. Yeah. And then another thing with that is, does their work actually exist? And where do we think we'll see it? So that way when we're going through our code base, we actually know, am I gonna run into this person or is this someone who I know was there, but I have to hunt for them? So knowing kind of that evolution of the code for your code base. And then with that, we also have code reviews. And that really affects what the code actually looks like because those people are impacting the code as we write it and as we deal with it. And the big thing with that is that idea that we don't talk about a lot of, you know who to put on a code review if you want the code review to be done tomorrow, and who to put on a code review when you want them to look at every line. And those are two different people. And you put on the appropriate person to get the thing done when you need it to be done. Who all's done that? Yeah. And so that makes it difficult because suddenly we have code that's at different levels of being looked at or has those different levels. And then the last W is why. So we need to understand kind of why they made the choices that they did and kind of, so that way we can look at the code and understand, here's what they did. We have those people who write really sloppy, fast C++. They get it done to about 85%. It works well enough, it gets through. And that's really important because sometimes we need that to be done in that way in order to get things shipped out, in order to get the product out to the customer, and that's important. But that's not also always what we need. And so we need to know when we look at the code, is this someone who was so thorough that we're gonna expect something weird? And that was probably something they thought about and something that they looked at versus this is something where they probably wrote it in a couple of afternoons and there's probably an error, and so we can expect that and understand what's going to come up. As well as cleanup. So if they're that person who cleans up the code around them, that's really helpful, but you also have to realize that they're changing kind of the meaning of the code as they're doing that. And so that way when we look at the code base, it's like, I'm doing a git blame, and then suddenly it's like, okay, I see that this person edited it. It's probably a cleanup comment or it's probably something else. So we kind of know how they ended up doing it. As well as architecting solutions. So sometimes people make things more complicated than they need to be, and sometimes people make it like way simpler than it needs to be, so then you start doing a solution and you're like, I have to re-architect the whole thing because this simple basic way doesn't expand into what I need it to expand to. So that's the end of the people. And then now we're gonna get into that big genealogy problem that we see in genealogy that's the same as in C++. So I'll let everybody take a look at this. I basically took a I took a US Department of Labor, their index records for being naturalized into the US, and I modified it for C++. So I'll let everybody read that. Cool. So with this, just to give a summary in case anyone's confused, we have that one legacy project that everyone calls the project because they don't really want to work on it. They know it has a lot of legacy code and no one really wants to deal with that issue. And currently it's in C++ 03, but it's existed since 1975. So it's been around a while. It's kind of updated a little bit, but it's trying. And in 2013, it got moved up to C++ 11. They just upgraded it, it's in C++ 11. And now they're trying to move it to the C++ 11 features in 2018. And they got denied because why would we end up moving things and changing up all of our source code in order to do it? And the people who we can talk to about this are a retired engineer who's currently chilling out in Hawaii, and corporate who decided that we need to start using all these new features. So this sounds a little bit crazy, but it's something that happens in our code and something that you can see in a variety of projects. So if we look at the C++ developer survey from 2023, we have C++11 and C++17. And we have large groups of people who either A, aren't allowed to use all the features in a different language, in a modern version of C++, or B, aren't allowed to use that version at all. So that kind of impacts, and that's the same thing that that other thing referenced. Those are the same thing. So with that, we're starting to have this divergence of, the whole idea of this is we're gonna take and make a timeline. So we wanna be able to chart our people and chart our code and go, okay, this aligns with the timeline of C++, and this will be awesome and we'll understand how C++ ends up meshing with it. Except that timeline isn't as simple as we think it'll be. So this is the technology adoption curve. And it doesn't quite line up, but it's kind of a good representation. So kind of the idea of this is looking at migration. So if we look at like how people end up migrating, if we look at like the Western expansion in the United States, not everyone ended up migrating during that period of time. There are those people who suddenly got the memo a couple months too late, and they're deciding to move over, and that doesn't quite line up. And we can see this with our C++ code. I mean, how many people in 2023 are running C++ 2020 or C++ 23? Not very many. And so our timelines don't quite line up. And so we have these groups of people who do it at about the same time, but not everybody. So this can create some weird offsets and make things really complicated and make it really hard to figure out kind of how our code works and what to expect. So then when we start doing git blame and going backwards, we look at the date and we go, oh, it's 2016. Like, we'll expect things. And then we'll look at the code and be like, this wasn't at all what we expected. And that was probably because of this. Because our timelines don't mesh as hard as we try and make them. So we're gonna kind of look at the two timelines here. We're gonna look at the macro timeline and the micro timeline. So the micro timeline is going to be that small Codebase timeline, try and characterize why our Codebase does the things that it does. So we're gonna look at the code changes, the workflow changes, and the documentation changes, and use that to kind of characterize our Codebase and understand what our Codebase is doing. And then we're gonna look at the macro timeline and look at kind of C++ as a whole and understand kind of why C++ is the way that it is, and use that because that influences the design trends and the patterns that we have to deal with today. Cool. So for code changes, there are a lot of different things that have happened in our code bases, and a lot of them aren't as pretty as we'd like to act like they are. So we've had language advancements from moving to C++11 to 17 to just like using different features. And there's a lot of reasons to why that happens. So when we look at our code, this can actually happen because there's that one person who's super excited and found that feature in, let's say, C++20 and is like, this is the thing, we need this. And someone else is like, okay, we'll just update it. And so that changes how our code looks. But then at the same time, that doesn't mean that everybody else knows how our code looks. Or the person who ended up watching a video and as soon as you see it, you're gonna end up implementing it everywhere. And then everybody else doesn't know what that is. And then we also have our internal code changes. So like if our coding standard changed, this will change kind of how our code looks and adds this level of confusion of what's actually going on as we're looking at our code. And so that can make it a little bit more confusing to figure out how to parse through it. We also have other programming languages. So if we have like C# or Java, those will influence kind of how our code will write, how we write our code, and how it actually looks. So different people will end up writing code and use different programming languages, and that kind of influences how our code base ends up looking and how it ends up working and how we end up going through it. As well as migrations and changing of the different languages, because that just adds another level of complexity that we're continuing to add on. Now, if you've noticed, this is a really messy picture, and it's something that's just as messy as trying to go through your family tree and figure out why someone did the thing that they did off of postcards. Like, that's not easy, and we're kind of going with the pieces that we have, and those pieces are very similar. They're just, one's a different medium than the other. Cool. Another example with this is the Gregorian calendar. So part of my family was doing, had the Julian calendar for part of their birthdays. And so when we look at our language advancements, we have, if we're looking at that calendar, when they came to the US, their birth dates were in a different calendar. So some people decided, we aren't gonna change the calendar, we aren't gonna change our birthday. We'll just leave it as it is, it's close enough. Some people decided to do the translation and they, let's say it was plus 5 days. They'll add 5 days to their birthday. Great. This is what we see with changing the coding standard and changing these things. People will either A, say, I'm gonna ignore what's sitting here and it's good enough, we'll just leave it. And then there are those people who say, we're gonna fix it while we're here. And then there are the people who fix it while we're here. And it's like doing that math on that calendar. Instead of adding 5 days, they subtract 5 days. And suddenly you have something that's not even correct, but we're just going with it and keeping on going. And so that causes chaos, and that's something that happens in your code. Cool. So now jumping into workflow changes. So this involves tooling, rewrites, and some of the major features. So with this, who has had a project where they've seen the first commit in source code? So you've gone all the way back and it's like initial commit from when they either migrated from like SVN or they started using Git or whatever they did. Who's seen that? Now that's a really nasty commit to run into because you want more information than you get, and then suddenly you're like slightly disappointed, but at the same time, at least you can find kind of what the code originally looked like, and hopefully you can figure out what's actually going on and what the intended circumstances were. Now, with that also causes a ton of problems because if we migrated and we dropped all the previous information, this is like in the US, there was a census and they actually ended up having a fire and they lost most of the census. And so now you have that issue of we're just missing a section of data that we need. And so this is something that happens in our source control too, of maybe we didn't migrate all of the data because it was a lot of data to migrate and maybe we aren't planning on using it. And then you're the person trying to go backwards and you're like, if only I knew what they did to this file. And you're like, well, got nothing. So yeah. So this is kind of where we start to run into issues with tooling and with auto formatting is like how the evolution ended up happening. We have to figure out based on these little crumbs that we're following backwards. Cool. And then documentation control or documentation changes. So our documentation ended up changing a lot throughout time and throughout C++. So when we're looking at things, we have our headers and comments. So who's seen one of those headers that takes up about half a page and has every engineer who's modified this piece of code with kind of a brief summary? So those can be kind of hard to look through. And I feel like our first instinct is to delete those and that they're completely useless because it doesn't have all the information that we need. Until we're trying to dig backwards and understand why someone did the things that they did, and it's in some random cleanup commit that we ended up deleting all this history. So this can cause things to be really weird, as well as we may have those engineers still in office, and they may have been promoted to another area, and so it's like, I could ask that person maybe if they remember what they were doing here, but now that I don't know why they were here because that whole comment was deleted, I lost all that history. We also have our external documentation, which as much as we all don't like documentation, we do a really bad job of keeping it up to date, as well as dealing with like where it's at or if it moved or keeping information because we tend to drop it off as long as it's not in the code. So this is kind of the summary of all the things in our local code base that are changing and dealing with along our timeline. So now we're gonna jump into the macro timeline. So with the macro timeline, we kind of have our C moving through all the way up to present. And as much as this is really pretty, one of the things that I figured out while trying to figure out how this talk works is that this is probably one of the least pretty graphs that you could end up doing. Because we have the committee trying to come up with new ideas, and these are all being inserted back in, and so it makes it really hard to figure out where people are actually figuring out things, as well as when someone listened to something or learned something influences when they actually ended up figuring out this stuff actually exists. So it's not quite as pretty as it seems, but I'm gonna try and summarize kind of the big picture of it. And this kind of goes off of Bjarne's talk this morning, because he went through some of that stuff as well. But this is kind of taking it and looking at our code base versus looking at what we can do in the future for the language. Cool. So first, C. So with this, we're kind of having that header block style code, as well as having all of our variable definitions at the top. And I feel like our first reaction when we see that style of code is to take that code and get rid of all the variable definitions at the top and start dropping them down and trying to figure out like, where's this variable actually needed? And like half of them are useless. And it's like, why did we keep this variable around? Because we clearly aren't using it for anything, but we didn't delete it because we didn't know what it did. As well as having a lot of macros and raw pointers. Cool. And then we start to progress into C compiled with the C++ compiler. And this is where you're getting some of the C++ comments and less typed Fs for structs. And we're starting to see that morphing of how we're writing code to kind of adapt and make sense. So we're starting to change our code throughout time. And this is something that like may or may not apply to your actual code base. Cool. And then we have pre-C++ 11. So this is where we start to get into object-oriented everything, which is basically we're going to make everything into an object, and every object is going to inherit from another object, and then that object will inherit from another object holding a couple of pointers to a couple of different objects. And by the time we're done, we have a lot of objects that we don't know why they're all related, but somehow they all kind of send each other around and we're trying to figure out what's going on. And this is a really big idea because end of the day, this is kind of like a trend. So we can look at this trend today. If you look at AI, what is everybody doing right now? AI. So when we start to look at it, we're starting to figure out that object-oriented everything is this pattern that we're overusing at this stage because end of the day, one solution doesn't work for everything. So we're going to need other solutions in order to figure out why our code works and how to write the most usable, maintainable code. And so to do that, object-oriented is a really important tool, but not the only tool in our software engineering toolbox to pull from. Going down the rest of the list, we also have exceptions. And exceptions are another one where we're starting to have that overuse of like, you look at it and it's like, we're just going to throw and catch exceptions everywhere. This is something you see if you take a C++ class today. The minute they talk about exceptions, you're wrapping things in try-catch statements that aren't that big. And so we're trying to figure out kind of how to use different things and having that overuse upon initial use, and then kind of scaling everything back to something that actually makes sense. We also have standard containers and this idea of building your own container, which with that, who has seen and still used a custom container today that could probably be replaced with a standard library container if someone wanted to? So with that, these are things that we came up with in pre-C++ 11 and have just kind of carried along with us as this baggage instead of taking and spending the time to rip it out, because end of the day, the standard probably tested that container more than anybody in our current code base could have. And so if we don't go backwards and figure out why this is happening and kind of get rid of it in order to make better code, better maintainable code, safer code, we aren't actually going to improve and deal with these legacy troubles that we're carrying on. And end of the day, we may actually find a bug that we didn't realize was there and just accepted. Cool. And then now we're going to get into early modern C++. So this is kind of grouping C++ 11 and C++ 14 because they're pretty similar and there's a lot of things and they can kind of get mixed up. So this is where we're having that smart pointer overuse, which is kind of going back to that original thing of just kind of overusing one thing. So we're just going to end up using it everywhere and it'll be okay. And that's not to say smart pointers aren't bad, but we're overusing them in this context. We also have scoped enums, so we're starting to kind of continue that language of evolution and try to figure out what's going on. And then another big one is move semantics. So we had the change from the rule of 3 to the rule of 5 here, which was a really big deal because end of the day, we're changing how we think about writing code and how code actually works. So if you look at code and let's say we have a bunch of engineers and not everybody knows why we moved to the rule of 5 and they upgraded. We're going to start to have code that doesn't quite align and we aren't using the features of the language because we don't actually know that it exists. And so we're starting to have this issue of we've created this thing where if people don't actually know what we're doing, we can't actually write good code and deal with the problems. Cool. And then we also have trailing return types. And this is kind of getting into that idea of as we look at different code throughout these different eras, it doesn't look the same. And so if we don't expect to run into that code, we won't know what we're going to see until we walk in there. And we look at it and we're like, this code looks completely different than C++ 03. And so how do we deal with that? Well, we need to figure out like what to expect in these different eras. With this, we're also having that shift away from books and towards writing, towards conference talks. So we're having the information kind of get to people in a little bit different of a way. Cool. And then to continue with early modern C++, we're also having kind of this big shift away from object-oriented and towards generic programming and functional programming. And this shift appears to be a little bit less drastic than the OO shift. The object-oriented shift tended to be a little bit more blanket across everything, and these tended to kind of compete with OO, and you're kind of finding this balance, which we're starting to find today of maybe we need a little bit of each thing in a variety of different areas, as well as having templates and all of that becoming a lot more present and trying to figure out kind of how we can write different types of code. Cool. And then continuing, now we're going to jump to 17. And 17 kind of changed the way that you look at code. So if you look at pre-17 code to 17 code, it's going to look very different. In a lot of ways, I think it looks a little bit more like some of the other languages that we see today. And the big thing with that is structured bindings. So you look at that and it's reducing the amount of overhead that we're having to do in order to look at different things and trying to change how we look at code. And this is really important for that genealogy aspect, because as we're looking backwards, we're trying to understand what the programmers were thinking. So this is something where if you see a structured binding and discover it for the first time, you kind of have this 50% chance that it'll go through. So if an engineer puts it in a code review, puts it up, and is like, look, this is a structured binding. It reduces all this bloat and it's so much easier to read. You're gonna have that 50% chance that the reviewer won't know what it is, will say, well, we aren't gonna use it because no one knows what it is, so why would we put it in the code base? And then that 50% that's like, you can just do whatever you want and someone else will figure it out the next time they find that piece of code. And then the other thing with that is you may have that no one actually knows how to use it, so you'll have to comment that this is a structured binding. You may want to look it up. And then we get back. Then we look back a couple years later, and it's, why do we have this comment and this is really redundant? And so we're kind of having this juggling of trying to deal with how our timeline moves forward. And in the present, this makes a lot of sense. In the future, it may not make a lot of sense. And in the past, we look at it and go, that's obvious, why would you ever have done that? And it's, well, we knew no better looking at where we were at then, and we're doing the same thing today. Cool. So then now we have postmodern, and this is another one where we're really changing how code actually looks. So like if you run into it and go look at a spaceship operator, and you're not expecting when looking at your operator overloads to see it, you're gonna be like, what is this thing? What is it doing? And how is this allowing me to write decent code? Because I have no idea what this is. And our root reaction when we see something like this is to go, we're not going to use it because this is weird, this is different, and I don't know what it is. And so this kind of influences how we're ending up looking at code and dealing with code. Cool. So this is the end of kind of that C++ timeline. But as nice as the C++ timeline is, and this is kind of a linear view of it, and it's like, cool, this works. Then we have all the external influences that kind of go into C++ and go into our code base and causes everything to feel a little bit more twisted and a little harder to understand. So with that, we have Boost. And the nice thing with Boost is that it ends up usually getting integrated into the standard library a lot of times. The bad thing with Boost is that if you don't realize it got integrated into the standard library, you could have upgraded and are just continuing to use the Boost one when you can actually move it and just like basically do a Control F and migrate it over to the standard. And that can make it a little bit easier because you have less of that third-party influence. But we also still have to understand that influences how our code works and how the standard library works and how we have to deal with all of those things meshing together. We also have that with kind of other languages and trying to understand like what's going on, as well as the standard takes in some of these other languages concepts and applies it to the standard to make the standard better for all of us. And so this kind of becomes this giant spider web of how do we figure out what's going on. So then when we start to link all the timelines together, we start to run into just because C++ is at this version at this point in time doesn't make our code bases. Just because we're running C++ 17 doesn't mean that we're actually writing C++ 17. Just because we're doing this doesn't make us at this point. But at the same time, we can be at multiple different points at the same time. You can be running C++ 17 and have never written a smart pointer, and that's okay. Is that the best thing to do? Probably not. But that makes it really difficult when we're trying to look back at code and understand what's going on and how we're doing it. So now kind of looking at how we're going to deal with the past. How we're going to process the past and figure out how to write better code for the future. Because at the end of the day, that's what we all want to do. We want to figure out how to deal with this past that we have to carry as this burden and try and figure out how to write better code so that way we don't have to deal with this burden maybe next time. So the first thing is redundancy. And redundancy itself is kind of redundant because as much as we try to keep things in multiple places, we never keep it up to date. And so there's kind of this double-edged sword of keep it in multiple places so that way we don't lose it, but keep it up to date, but then we're never going to update all the different places and then suddenly no one's ever happy. But with that documentation is really important and knowing what's up to date and what's not. So if you're working on a feature, that documentation is probably isolated to that feature documentation that may be external. So like maybe on Confluence, maybe somewhere else, how we ended up choosing to do that feature. But we need to be cognizant of, here's the things that we chose not to do. And highlight that of like, we didn't do this because of these things. And so that way we aren't looking at the code being like, I can't tell if they did this, if we deleted it, if whatever. But we know at that point in time, this thing wasn't actually implemented. So we kind of have that grounding stop. And then we also have all the other documentation that we don't actually think of as documentation, but is super important. So we have things like the code, and we can have our self-documenting code. We can have code that makes sense, that you can read it, that you can understand what's going on and why we're doing the things that we're doing, as well as code review, writing code, looking at code, trying to we can go back to the code review and go, okay, here's why people thought the things that they did. Or, oh, someone asked this question. This is the same question that I was about to go change and maybe create a bug, and that's why they did that thing. And then commit messages. So if you write a good commit message, suddenly in the get blame, it makes it faster to figure out, oh, this is why they did the things that they did. So we kind of need all those different pieces in order to have good documentation that we can kind of carry with us as we end up writing code and using code. And then with documentation, we need to kind of figure out how to write good documentation and deal with old documentation. So we really don't want to leave partial traces of the past. And this is something that we're all known to do. You're looking at an old piece of code, you're editing it, we have to make a one-line change. And it's in the middle of, let's say, a for loop. And you look at it and the comment is completely wrong at the moment. But you don't quite know what it's doing. And you're like, I just need to change this one line to have this one number be a little bit different. We usually end up leaving the comment and being like, it's somebody else's problem. But by doing that, we're just creating the same problem for ourselves in another week. So we need to kind of take it upon ourselves to go update the code and figure out what's actually happening and update that comment. Maybe that comment doesn't need to be there. Maybe that comment needs to be reworded. Maybe it's kind of only part of the truth. And so we need to deal with that. And with that, we kind of owe a thing to ourselves of knowing what the code is doing. If we don't understand the code, we can't actually write good software and understand what's going on. And that's a little bit deeper than understanding, oh, in this part, I need to make it a for loop. Because if we don't know why we're making it a for loop, we don't understand what we're doing. So we need to really understand not just what we're doing, but why we're doing it. So if we're trying to accomplish this bigger picture, then we understand what we're looking for. And this can be connected back to genealogy of, I've been looking at one of my ancestors going back to their homeland after immigrating to the US, and it's, why am I looking into that? Well, they were supposedly on the Titanic, but they chose not to get on it. And so I'm trying to figure out why they didn't get on that. And that's kind of this mystery. And so if we don't know why we're trying to do that, then suddenly we're just looking for this random travel form and there's no real reason why it's important. And that's the same thing with our code. And so we kind of have that O to try and figure out why we're doing the things that we're doing and how we can do it better. Cool. Yeah. And then for interfacing to existing code, we have to figure out that sometimes we may not be able to write all the code, and we need to figure out this code is actually working and we don't need to change everything. We just need to change this one little thing, change a comment, and it works perfectly fine. And then sometimes we look at it and go, this was 2003 C++. We need to update it, and how they did it doesn't quite express intent. And the only way to do that is to completely rewrite the code. And so we'll need to deal with completely rewriting the code to deal with that. And then for cleaning up the code. So we want to figure out the best way to clean up the code without ruining all that data. That's the same as going to your grandparents' house, dealing with all the random family history stuff and deciding what stuff do I throw away because there's a lot of stuff and just like random stuff versus what stuff is really important here and is stuff that like the next generation is gonna be like, why did that disappear? And that's something that like, if you've ever looked at that, no one knows the right answer for. And everyone's like, well, this is a really rough battle of what actually do we need to keep? And so with that, there's a big cost. It takes time, it reduces our ability to actually go see the customer, deliver valuable product in order to clean stuff up. But then we'll have that moment where everything is so bad, our requirement is to clean stuff up. And that's less productive than cleaning stuff up in the beginning and actually dealing with it that way. So we need to end up dealing with it earlier. Good. And then with that, we can accidentally cause bugs to stable code and have a distortion of our history, and it makes it even harder to read. So this is kind of this double-edged sword of how do we end up cleaning things up better, but also understand that we're actually tampering with the history that we want to protect and save. And so a lot of that is being really explicit about where we're cleaning stuff up and where we're not, and why we're cleaning up the things that we're cleaning up. Cool. So how to implement all these things? So to implement all these things, we're going to end up needing to ensure that we have all the testing. Because if we don't have all the testing, we're just going to cause a lot of bugs. As well as ensuring that we have the boundaries for cleaning up. Because the minute we don't have boundaries and we're looking at old legacy code, you look at one little section, and that one little section ties back to another function that ties to another function, and suddenly you've changed over 100 files, and everyone's looking at that code review like, why did you ever do this? And you're like, but it made sense as I'm working down the tree. And so that makes it really difficult, and we have to have those really hard boundaries to ensure that we're actually cleaning up the right things and cleaning up the things that are important for looking at code in the future. And then we also need to make sure to separate out that cleanup from our ordinary feature work. Otherwise, we're just going to create more confusion for someone who's looking back at the history and going, why did this happen? Oh, it was to add this new feature. And it's like, actually, it was because we chose to clean up the code because that's what we needed to do in order to make code better. Cool. And then, so how we're going to actually end up doing better in the future. So we've figured out how to deal with the past code, but now we need to write our code better. And a lot of that is kind of reflecting on the things that we see and figuring out, like, we do make mistakes, so how do we make less mistakes and how do we write better code? So to do this, we really need to think before we act. We need to look at it and document our decisions so that way they stay up to date, as well as understand why we're doing the things that we're doing. Because end of the day, we have this trend of, is this a fad? Is this the coolest thing? Or is this the right decision that we need to be doing today in order to solve this issue, to create maintainable code, to do these different things? And if we don't know why we're doing those things, we can't end up writing good code. As well as we need to learn from our own mistakes. I mean, how many times has anyone written a piece of code and then left it for maybe 3 months, gone back, looked at it, and the Git blame says you edited it. And you're like, I don't know why I would have ever written this code like this, but it's you. Yeah. So we need to learn from those mistakes, as well as learn from our friends and our neighbors' mistakes in order to continue to write good code, as well as continue to write high quality code and commit messages, and understand that that is something that we need to do as much as we don't want to do that. Because end of the day, we're software engineers and we want to write software and not write documentation. But if we write the right documentation in a high quality way, that limits the amount of documentation someone else is going to have us write, because we need to deal with those legacy problems in the future. Cool. So that's all I have. Are there any questions?
So you said separate out the cleanup and the features that you're writing. What does that look like logistically? Like, how big of a cleanup does it have to be before you start a new branch and then, you know, merge that branch back in, or do you create a separate merge request before you do your feature?
Yeah, so I think that's something where, as you're ending up working through it, you'll look at a section of code and you can tell how legacy this code actually is versus how new this code actually is. So as we're looking through it, understand, is this something that we need to change, or is this something that we don't need to change? So if it looks like there's a ton of legacy code to clean up, maybe that's something where we need to break it up into something that's a little bit bigger of a task versus maybe that's something that's small enough that instead of it being on a separate branch, we can make sure that it's in a separate commit and pretty well documented, at least in the code review side, so that way we know where that information is going. Does that answer your question? Cool.
Hi. You mentioned how sometimes you do have to do things like large refactors or reformats, things that you would rather keep out of the commit history in a sense. Like you don't really care that those things happened when you're trying to explore like why a feature was added or like why a bug was fixed. Do you have any recommendations for how to mark those commits as being kind of separate and preferably ignored when you're digging through the commit history?
So with git blame, you can ignore specific commits. But with that, there's also this nice thing of if you do see that it's a formatting commit, you can always go backwards and look at it. But sometimes when we do those big formatting commits manually, we do have a chance of actually inputting and adding some new really subtle bugs. So that can be nice to know this is where something could happen. If you've looked at the Clang format, the actual the man page or whatever, it says in it there are some specific ones where if you toggle them on, this can change your code's behavior accidentally. So understanding there are areas where as much as we want to hide that this stuff happens, knowing that it happens and knowing this can be a source of error can be really valuable. Does that answer your question? Cool.
So along those same lines, like how would a genealogist write tools differently than a software engineer?
So I think a genealogist is kind of focused on understanding the past and understanding what's going on. So I think in a lot of ways, when they'd end up writing a tool, it would be a lot more focused on making sure we're understanding the changes that are being made and how it has that impact, rather than looking at the outside, how it looks after we do those changes. So I feel like in a lot of tooling cases, we end up being like, we want it to look this way, so we'll figure out how to make it look this way, or figure out how to notice that this is an issue, versus looking at how do we take the things from the past and understand why the things were done, and then how to move it to the future. So I think it's kind of your mindset going into the tooling, although I think they can produce the same results.
Hi, great talk.
Thank you.
Yeah, I come from a field of numerical analysis, numerical linear algebra, where there are a lot of code bases that are 40 years old or more, so it's normal to work with old code.
Okay.
How do you get less experienced developers, younger developers to feel confident working with older code?
So with that, I think a lot of it is having the trust on the younger developers. So I think with legacy code, we have this tendency to be like, I know this code base. This is a code base that I have jurisdiction over, and you weren't here to see these changes, and so we're gonna hold on to this and protect it. And that's really important to protect that history. But if we don't share that history with other people, then they don't have the confidence to go on their own. So that's letting them kind of make some of those decisions and do some of those things where it's like, maybe they saw it in school or something that's a really cool idea, taking that, running with it, and understanding it may not be the best idea, but it's moving the code base forward. So if we take that feedback and those skills, then that allows them to feel more comfortable in the code base and know that they can make changes and not be dependent on someone else. Because the minute we hold them from making any sort of implementation changes or any sort of ideas of maybe this algorithm could be simplified, then we're limiting their ability to do work and making them feel like they can't actually be successful here because we aren't letting them make those changes.
Great, thank you.
You're welcome. Cool. Are there any other questions? Cool. Thank you.